Hello Chem 1 and welcome to Practice Quiz version 3.2, an annotated experience. So a lot of this quiz is based around oxidation and reduction chemistry. And in order to do oxidation and reduction chemistry, we need to understand oxidation numbers. Okay, so for oxidation numbers, in order of importance when assigning them. So in a compound, certain elements have reliable oxidation states. So a compound is a mixture of two or more different elements. So first, remember things in group 1 in a compound tend to have a +1 oxidation state. Fluorine tends to have a -1 oxidation state. Oxygen, unless paired with another oxygen or in a peroxide, or technically if paired with fluorine, tends to be -2. And then finally, all the numbers need to add up to the overall oxidation state. So let's start with our NO3 2- here. So, and that's actually a typo, it should have been NO3-, but we can still complete this. So, since there are no group 1 elements, we'll start first with the oxygen. Each oxygen is going to be -2. So I like to put the individual oxidation numbers above the atoms. So each oxygen is -2, we have that up there. But there's 3 of them, which means there's a total of -6, but charge from there. Then remember that all the numbers need to add up to the overall charge on the molecule. So since the overall charge is -2, that means that the nitrogen must be +4. Okay, so for the next one, sodium carbonate. Now in this case, we do have a group 1 element, sodium. So we're going to start by assigning oxidation numbers to that chemical species. Each sodium is going to be +1. Group 1 elements are very limited in the oxidation states they can take on in a compound. Since there's 2 of them, it's going to be a total of +2. Now the oxygen is going to be, each one is going to be -2. But there's 3 of them for a total of -6. And since this is a neutral compound, that means all of these values, if we add them all together, they need to equal 0. So we've got -2, and we've got -6, which means the carbon must be +4. Okay. And then finally, that leaves us with this last one. So we have a group 2 metal in here, and group 2 metals are kind of like group 1 metals in that they're very narrow in the oxidation states they can take on in a compound. So our calcium is going to be +2. There's only one of them, so it's a total of 2 positive. Our oxygen, each oxygen is -2. And there's 7 of them for a total of -14, which means that chlorine, so collectively this is a neutral compound, and we can see that, so this has to add up to 0 total. So that means that chlorine must have a total charge of +12, because then the calcium and the chlorine together would be +14, and that would counterbalance the -14 from the oxygen. But there's 2 chlorines. So we're going to take that 12 and we're going to divide it by 2 because we're trying to find the individual oxidation states, the oxidation states on each atom, which means each chlorine here is in its +6 oxidation state. In this problem, we're given 3 different redox reactions, and we have to identify what's being reduced, what's being oxidized, what's the oxidizing agent, and what's the reducing agent, and then how many electrons are transferred in each reaction. So let's start by identifying the oxidation state on all the chemical species. These are some smaller, compound or molecules consisting of 2 atoms or just monatomic ions. So this will be a little bit easier to assign oxidation states to than the previous slide. Cobalt, any metal by itself, really any element that's neutral by itself, is just going to have an oxidation state of 0. So then on the flip side, anytime you have an ion that's just one atom with a charge on it, So here we have our cobalt with a 2 plus. The oxidation state is just going to be equal to the charge on that ion. So this makes our job nice and easy. This is just going to have a charge of 2 plus. Now let's look at the hydrogen. So the hydrogen, kind of a similar deal here. The hydrogen has a positive 1 charge. So that means its oxidation state is positive 1. And then over here, we have elemental hydrogen, H2. Anytime you only have one element and it's in a molecule that's neutrally charged, it's just going to have an oxidation state of 0. Okay? So, what's being reduced and what's being oxidized? Well, we can see here. I always like to identify what's being reduced first because the name tells us what's going on. We're going from positive 1 to 0. That number literally gets smaller. It literally gets reduced. So our H plus is what's going to be reduced. On the other hand, whatever is oxidized goes from a lower oxidation state to a higher oxidation state, which means our cobalt, solid, is going to be oxidized. It should be noted in these problems, whenever we're identifying what's being reduced and oxidized, and whenever we're identifying the oxidizing agent and reducing agent, we're only actually concerned with the reactants here. We need to look at the products to figure out how the charge was changed. But when we're identifying what's being reduced, oxidized, the reducing agent, and the oxidizing agent, we're only interested in the reactants. So then remember, whatever's oxidized is actually the reducing agent, and whatever's reduced is actually the oxidizing agent. So as long as you remember that rule, you'll be good to go with assigning the reducing agent and oxidizing agent. Finally, we have to address how many electrons are transferred in this reaction. And to do this, we can either hone in on what's being reduced or what's being oxidized. These are all balanced reactions, so there's no need for us to worry about looking at the half reactions here. So I'm just going to look at the cobalt because the cobalt only has one atom of it, so it's going to be pretty easy to figure out how many electrons came from it. One single cobalt went from 0 to 2 plus. So that means that that cobalt must have lost 2 electrons. Likewise, we can look at the hydrogen if we want to. There were 2 hydrogens, each with a positive 1 oxidation state, and then here they end up both going down to 0, which means each hydrogen must have gained 1 electron, for a total of 2 electrons. So we can hone in on either reactant to figure this out. For our next set of molecules, fluorine is in its elemental state here. It's just a neutral gas, so each fluorine has a 0 oxidation state. And then when it becomes the fluoride ion, we can see that each fluorine has a negative 1 charge, so it has an oxidation state of negative 1. The chlorine, on the other hand, goes from having a negative 1 oxidation state because it is those ions just featuring one individual atom with a charge, and it's going to its elemental neutral state, which is 0. So once again, we can identify what was reduced and what was oxidized. I'll start with what was reduced. The thing that went from a higher number to a lower number, well, that was our fluorine. So the fluorine, literally the number was reduced, and then that means that our chloride must have been what was oxidized, aka our reducing agent. And once again, as with last time, let's take a look at the fluorine here. So the fluorine, there's 2 fluorines, each with a 0 oxidation state. And after it reacts, we get our 2 fluorines, each with a negative 1 oxidation state. So since 2 fluorines went from 0 to negative 1, that means that each fluorine must have gained 2 electrons. Okay, one more to go. Okay, and now on to the last one. So each iron is 3 plus, and we can see that it's going down to the neutral metal, which is just 0. Then we have our tin, Sn. It's starting at 2 plus, and then it's actually going up to 4 plus. So what's being reduced and what's being oxidized? Well, we can see going from 3 plus to 0, that number is quite literally getting reduced. So this is what's gaining electrons. And then meanwhile, what's being oxidized? Well, our tin, because it's going from 2 plus to 4 plus. Now, in this case, we have to be careful with the number of electrons because, so we can look at either element when looking for the number of electrons lost. Just keep in mind, though, that we also have to keep in mind these coefficients. So iron is going from 3 plus down to 0. So each iron is gaining 3 electrons. However, there are 2 irons involved here. So that means that we need to multiply that number by 2. So total, so each iron is gaining 3 electrons, and total we have 6 electrons transferred. We can also look at our tin. We have 3 tins. Each tin is losing 2 electrons to go from 2 plus to 4 plus, so that matches up nicely. In this question, we're trying to find the reduction potentials of a number of different chemical species. So what we're trying to do here is we need to use our table of reduction potentials, the half reactions, and find the corresponding reactions that go with each of these different either ions or molecules. So let's start with sodium. Sodium can be reduced. We can add an electron to it, and when we do, it forms solid sodium. So then if we look up the reduction potential for this, it's a really unfavorable negative 2.71 volts. Remember, the more positive the voltage, the more favorable the reaction is. This is really not favorable, which is why when we encounter sodium IRL, it tends to be in, say, sodium chloride, like salt, where it's in its +1 oxidation state, and not in lustrous solid sodium. Okay, up next we have iron. Iron 2 plus specifically. Iron makes a few appearances on there, but we're looking specifically for iron 2 plus. And we can reduce iron. And the reduction of iron, a little bit more favorable. It's negative 0.440 volts. In terms of metals, iron somewhere in the middle can be reduced. It can be oxidized, unfortunately. We can make rust out of it. Okay, up next we have chlorine. Chlorine is a halogen, and halogens love to be reduced. They love having that -1 oxidation state. So these can take on electrons to become 2 chloride. And this comes with a positive voltage, positive 1.359 volts. Really favorable. And then finally we have silver plus. So silver, just like the other precious earth metals, like for example gold, really easy to reduce, wants to be in its 0 oxidation state. So this has a positive 0.799 volt potential to go with it. Okay, and now what we're doing after that is we're trying to rank these from worst oxidizing agent to best oxidizing agent. So we're trying to rank them from the one that wants to be reduced the least to the one that wants to be reduced the most. So now all we have to do, we've actually done most of the work at this point. So the way that we're going to rank them is the one that's going to be the most favorable is going to be the most positive. Most positive equals most favorable. Whereas the most negative one, this right here, is going to be the least favorable. So when ranking these, we'll end up getting the order that sodium plus is the worst. After that, iron 2 plus. After that, we have silver. And then finally, the one that's most readily reduced, therefore the best oxidizing agent, is chlorine. And that's how we can rank them. And we'll do the same thing with oxidation potentials and reducing agents in roughly now. So we already took care of this top part. Now we're on to ranking these various oxidation reactions. So let's get to it. Okay, so with oxidation potentials, we actually need to flip our reduction reactions. So what I mean by that is, if we look at our, let's start with gold, Au. So if we look at the reaction on our reduction potentials table for gold, it's Au plus aqueous plus an electron yields Au solid. So the key is, whatever species we're looking for to see its oxidation potential, for our reduction potentials table, it should actually be in the products because we're going to be flipping around these reactions. So the first thing that I would do for any of these is look for this particular chemical, Au solid, and remember the oxidation state is important here. Look for it in the product side of those reactions. So this has a standard reduction potential, E standard of reduction, of a cool positive 1.69 volts. So now, the question is, what is the potential for oxidizing Au solid? So we're flipping that reaction around. When we flip around the reaction, it becomes Au solid, turns into Au plus, and that's aqueous, and it gives off an electron. So, whenever we flip a reaction, remember the voltage also flips because we're doing the opposite reaction. So this is negative 1.69 volts. Not very favorable. And this kind of matches what we know about gold. Very rarely do people complain that their gold has rusted, that their gold is oxidized, because it's very, very difficult to take electrons from gold. It takes a lot of voltage to be able to do it. Okay, so with iron 2+, we're looking for iron 2+ as a product, and we're flipping the reaction. And the only way that we could do that is if we turn it into iron 3+. So it's going to be giving up one electron. And when we find the reverse reaction on our table, this is going to be negative 0.771 volts. Also not super favorable. Up next we have fluoride. So good luck oxidizing fluoride. Fluoride is the most difficult thing on our table to oxidize. It is at the top of our reduction potential tables. Fluorine loves to be reduced. It loves to be F-, making it become F2 gas. That's going to take, well, you need 2.87 volts in order to do that. So then finally we have lithium solid. Finally, something that wants to be oxidized. It can turn into lithium plus. It will lose an electron in the process. And that has a very, very favorable whopping 3.05 volts. Okay, so now if we rank them, we're ranking them from, we're trying to find, oops, my apologies here. I meant to ask the question, rank them from from worst to best reducing agent. My apologies for my typo here. Because we're looking at oxidation potential, we're considering them being reducing agents, not oxidizing agents. Sorry about that. And now what we're going to do is basically take the same exact approach as before. The more negative the voltage, i.e. this one's the most negative, the less favorable it is. So we're going to rank that one last. Then, gold. After gold is going to be iron 2+. And then finally, the only one that's truly pretty favorable here is going to be our lithium solid. So now we're putting together what we did in the previous two sections. We're combining a reduction and an oxidation, and we're trying to find the overall voltage. So first we need to identify what's being reduced and what's being oxidized. So I guess this is actually combining what we did in the past three sections. So our H+ is being reduced, our iron is being oxidized. And now what I'm going to do is I'm going to write out each of these individual half reactions, and we're going to find the voltage associated with it. So, for our reduction reaction, the half reaction, we're taking H+, like so. We're adding in 2 electrons to make it H2 gas. Right? The standard reduction potential for this half reaction is, well, this is actually kind of the gold standard because this one is 0. This is the one that's used as the sort of barometer to distinguish between positive and negative voltages. All other voltages are with respect to that particular reduction. So then our oxidation reaction is, we're taking iron solid and we're oxidizing it to be iron 2 plus aqueous, and we're kicking out 2 electrons. And the E standard of oxidation for this particular reaction is positive 0.440 volts. So then finally, to get the overall potential of this cell, the E standard of the entire cell, what we have to do is add together the reduction potential of whatever's getting reduced, plus, so to get the overall E standard of a cell, we have to add the reduction potential of what's being reduced, plus the oxidation potential of whatever's being oxidized. So in this case, we're going to add together the 0 volts from the reduction and the positive 0.440 volts from the oxidation. And when we do, we'll end up getting positive 0.440 volts. And my apologies, I think there was a slight recording error there. So I'm just going to backtrack to make sure that I said all of this. Whenever you want to find the overall E cell, the overall voltage of a cell, add together the reduction potential of whatever is being reduced, plus the oxidation potential of whatever is being oxidized, and that will give us our overall voltage for the cell. So, the last thing is, this says, is it spontaneous? This is a resounding yes. Positive voltage means it's spontaneous, and spontaneous means, yes, indeed, it can do work. So whenever we have positive standard voltage, that means it is indeed spontaneous under standard conditions, and that means it can do work under standard conditions. If it's negative, it means vice versa, no and no respectively. Okay, so now we have some halogens reacting. We have chlorine trying to take some electrons from fluoride. Let's see how that works out for chlorine. Good luck. So our reduction reaction is the chlorine going from Cl2 gas, trying to take 2 electrons and become chloride. Okay, so that has a standard reduction potential. We can look on our table of negative 1.359 volts. Positive 1.359 volts. So that in of itself is generally pretty favorable, but we have to consider the other half reaction that's going on here. We have to consider fluoride as well. So the oxidation is going to be 2 fluorides, 2 F minuses, losing their electrons to become fluorine gas, and the 2 electrons. This has an E standard of oxidation. Since we're oxidizing the reaction, we have to flip the reaction that's given on our reduction potentials table of negative 2.87 volts. Really, 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 really difficult to do that. So, while reducing chlorine ordinarily is doable, the reducing agent has to be something better than fluorine because, this really isn't going to work out so well. When we add these two together, we'll get our E cell, which is, we get negative 1.511 volts. So, now we've got negative voltage, so is it spontaneous? Nay, it is not. Can it do work? That is nay as well. Negative, Ghost Rider. Alright, we've got one more. Lithium and sodium reacting. Let's do it. The reduction is going to be sodium going from its positive 1 oxidation state, and it's gaining 1 electron to become solid sodium. This has a reduction potential of negative 2.71 volts. Very, very difficult to do unless you have a potent reducing agent. Well, let's see if lithium's up to the task. So, we have lithium solid that we're oxidizing, And when we oxidize lithium solid to form lithium plus and lose an electron, this has an oxidation potential of positive 3.05 volts. That's wildly, wildly favorable. So it turns out that lithium, if we pair lithium and sodium, it's going to be enough to put that electron back on sodium. Independently, neither one of these chemical species really wants to be in its solid neutral state. But if you've got something that's so easily oxidized like lithium, you can do this. So that gives us an overall cell potential of 0.34 volts. Is this spontaneous? Yes, it is positive. Can it do work? Yes. Positive voltage means indeed it can. Okay. So then the last two questions are: what type of reaction takes place at an anode? What type of reaction takes place at a cathode? There's a number of different mnemonics you can use to remember this. There are like LAN-ox and G, a red cat. G, the red cat, means reduction at cathode. Anyway, the way that... So anytime we have a positive voltage, something is spontaneous and can do work. So the last part of this page says what type of reaction takes place in an anode, what type of reaction takes place at a cathode. In order to answer that, there's a number of mnemonics that you can use. You can use like LAN-ox and G, a red cat, which means reduction takes place at the cathode. I like to think of it more as electrons travel in alphabetical order. So they go from A to C. And what I mean by that is the side where they leave is the anode. That's where oxidation takes place. Where the electrons are going, that side gets more negative. That's where reduction takes place. So, what takes place at an anode? That's going to be oxidation. And what takes place at a cathode? That is going to be reduction. And that's true for any type of cell. In this question, we have three different ions. We have sodium plus, we have chloride, and we have calcium 2 plus. And our question is, which way are they going to be drawn by the forces of the chemical concentration gradient and the electrochemical gradient? So, basically, the two key ideas here are as follows. For the chemical concentration gradient, our chemicals are going to move from high concentration to low concentration. So this is sort of like the idea of diffusion. The more concentrated side is going to get lower in concentration as the ions move toward the more concentrated side. So with that in mind, let's figure out which way these ions are going to be drawn according to their concentration gradient, their chemical gradient in each of these cases. And to do that, we're just really going to count the number of ions. We're assuming that these cartoons are proportional to the actual concentrations on each side of the membrane. So what we're going to do, for example, with calcium is, on this side, there are 4 calciums. And on this side, there are, wait for it, 0 calciums. So according to the concentration gradient, the calcium is going to go that way. Okay, up next, let's do sodium. On the top, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sodiums. And on the bottom, we've got 1, 2, 3, 4, 5, 6. So, the concentration gradient is going to be the higher concentration to lower concentration. So this is going to move downward. Then finally, let's do chloride. Okay, so we've got 1 chloride down here on the lower side. And on the upper, we've got 1, 2, 3, 4, 5. So that means that we're looking at this direction, downward, from more concentrated to less concentrated. So that's for all of the concentration gradients. Now let's do the electrochemical gradient. For electrochemical, it's going to be cations are drawn toward the more negative side, or at least positive if there isn't a truly negative side. So basically the electrochemical gradient just states what we know about ions. Opposites attract. Negative charges go toward positive charges go toward negative charges. So for anions, it would be the anions are drawn toward the more positive side. So basically what we're going to do is count the total charge on each side, and then we're going to choose which side is more positive and which side is more negative. So if we look at the top, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 sodiums. Counterbalancing that charge, we have 1, 2, 3, 4, 5 chlorides, which gives us an overall charge of positive 4. Let's see how that compares to the other side. We have 1, 2, 3, 4 calciums, each one with a 2 plus charge. So we have positive 8 total from the calcium. For the sodium, 1, 2, 3, 4, 5, 6. And then finally there's only one chloride with a negative 1 charge. So that means that this side, if we add all this up, we end up getting a much more positive value. So on this side, the overall charge is positive 13. Okay, so this is the more positive side, and this is the more negative side. That means that the cations, calcium and sodium, are going to be drawn toward the more negative side, the less positive side. So for calcium and sodium, they're going to be drawn in terms of their electrical gradient. They're going to be, you can kind of think of it as being pushed away from that more positive side, whereas the chlorides are going to be the opposite. So the chlorides are going to be drawn this direction, toward the more positive side. So for those keeping score at home, if we look at chloride by the electrical gradient, again, chloride by the electrical gradient is going to be drawn toward the more positive side, which is going to be downward. And by the chemical/concentration gradient, it's also going to be downward, from the more concentrated to the less concentrated side. Sodium by the electrical gradient will be drawn toward the less positive side, the more negative side, upward. But its concentration gradient goes the opposite direction, because it's very concentrated with sodium on the upper membrane and not so much on the lower. And then finally for calcium, calcium is going to be the same story with regards to the electrical gradient. It's going to be drawn upward for the electrical gradient, but also according to its concentration gradient, because there's a lot more calcium on the lower side of the membrane than there is on the upper. Okay, and our last question. You just want to know a little bit about the general setup of a neuron. You want to know how to label these 3 parts that are given, and also just know their general function. So let's take it from the top, and by top I mean the dendrite, and we'll go from there. So these are the dendrites, kind of like the wispy part. You can think of them as the palms of the sideways palm tree. And their job is to receive stimuli. This is where the input goes. So that stimuli might come from some sort of electrical signal. It might come from some sort of neurotransmitter. But this is where the signal goes in, etc. Then the signal travels to the axon. The axon is basically where the signal gets sent down the neuron. So this is what propagates the signal down the neuron. And for our purposes, we just want to understand that this sends an electrical signal down the cell. So the signal starts at the dendrites, and it moves down through this electrical signal that's caused by the movement of ions, and it goes down toward the end where it reaches the axon terminus. The goal of the axon terminus is to then take this signal and spread it on to either a different neuron or some sort of action point, like maybe a muscle, tell it to contract or something like that. So this keeps the signal going, and here I'm going to draw in some incredibly realistic cartoons of neurotransmitters. Okay, and that is a neuron in a nutshell. And that concludes the material from this practice exam. Go forth and dominate the actual exam. Thank you for your time. Have a great day and a dominant quiz.